Hello everyone, welcome again to my SAS tutorials. This is lesson 9 and I'm going to be talking to you about the frequency procedure today. Specifically, I'll be showing you how to do a chi-square test, a Fisher's exact test, and to get estimates of an odds ratio or a relative risk when the outcome is rare. I'm going to be using the SAS help manual as example here, and to get to it all you have to do is push the F1 key or go to help and click up, the SAS help and documentation button. That will give you this menu here, and to get to the example we'll be talking about, hit this search button, type in chi-square, scroll down to where it says the frequency procedure, double click that. You'll be getting a table of contents here, and the example I'll be using is right here under this analysis of a 2x2 contingency table. So here SAS gives you a data set that represents a case control study in which they have a high-fat diet and they're trying to see how it affects the risk of a coronary heart disease. And to continue this example, just go ahead and copy that, or copy the code that I have in the menu below the window, and go ahead and input it right in, paste it right into SAS. Now, the thing that I really like about all of these SAS examples is that they're very well organized, and they always have what you should ideally do with a data set. So here the ideal is to make sure that you always have a format on your values. So here for the exposure format, they're showing that a 1 represents the high cholesterol diet and a 0 represents the low cholesterol diet. And the response, or the outcome in this case, is a 1 means that they did have a coronary heart disease outcome, and a 0 means that they did not. So that's a typical 2x2 contingency table coding for your rows and columns. The thing that they also do differently in this example that I wanted to point out is they have a different way of inputting the data set in your data step. And it's a really efficient way of doing it, but it's only really useful if you're doing 2x2 contingency table analyses, or this kind of odds ratio or relative risk calculation type stuff by itself. But in the real world, you usually have data sets where every row represents a different subject, or a different patient, or a different machine, and so usually you have the exposure and outcome as separate variables and not using this count. So this count is basically saying that if you have a 0 exposure, as in this case the low cholesterol diet, and a 0 outcome, in this case a non-coronary heart disease outcome, then there were 6 people who fell into that. There were 6 counts of this exposure outcome pairing. And so they do that for every possible outcome here. So low-fat diet with no CHD, low-fat diet with CHD, high-fat diet without CHD, and high-fat diet with CHD. And so they show the counts there. I've rearranged a little bit of the actual examples coding so it's a little bit more efficient. And so you can see here I've added this label for the diet type. I've renamed their response variable to outcome, and I've added a label for the count. So I say here are the cell counts. I've also moved this format for the exposure and outcome up from, they did it originally in the procedure. I copied it into the data step, so it's all right there, nice and clean for you. And once you run it, you can also confirm, as before, by clicking on Libraries, Work, and seeing that the FAT comp data set was created. And if you want to see what it looks like, you can just go ahead and double click that and see it's right there. So it's nice and pretty. Now the thing about contingency table analyses is that you want to use this frequency procedure, but you also want to make sure that when you look at the table that the column represents the independent variable, the dependent variable, in this case the outcome, and the rows represent the independent variable, in this case the exposure. And so before we even get into the frequency procedure, we also want to use this Proc Sort, which just rearranges the order of those row and column headings so that they're easier to read in your final 2x2 matrix. So go ahead and run that. And here's the code for the Proc FREQ. Now I added some notes above here just to help you as you're going along. The frequency procedure produces row by column tables defined in the table statement. So that's this right here. To make sure that it's a 2x2 table, you just have to specify this asterisk in between your independent and then dependent variables, or your row and then column variables, to make sure it's a 2x2 matrix. Often when trying to see an association between two variables, it's common practice to list the dependent as the column and the independent as a row. I don't know if that's required for doing chi-square tests or odds ratios, but it's just something I learned in my epidemiology classes, and it's just nice to do that to keep it consistent with other studies. The exact statement here, this requests that you get Fisher's exact confidence limits for the chi-square test, which I'll show you in a second, or for the odds ratio. And the thing you need to know about the odds ratio is that that's this OR here, once you get an odds ratio from a frequency table analysis or in actually hand calculating it, that you can actually say that the odds ratio is the relative risk if the outcome or the disease state or whatever is a rare event. In this case, I believe coronary heart disease counts as a rare disease, maybe not in the US, but probably across the world. And so you can say basically that the odds ratio would be approximately a good estimate for a relative risk. Here, the title statement that they include, and I've just shown you, I've just copied it here so it keeps it consistent, just allows you to make your frequency tables look a little bit more professional. So when you're seeing your output, you can tell right away what the table or what the frequency represents. And here it represents case control study of high-fat cholesterol diets. So if we go ahead and run this, oh, and one more thing, this weight statement. This weight statement is used because of the way we coded our data set. Remember that we use this count variable to say that every one of these pairs represents 6 cases of 0, 0, or 2 cases of 0, 1, and so forth. And so it makes a lot more sense if I go ahead and run this and show you what the actual 2x2 table matrix looks like. And here it is. It's basically all of this part. And you can see here that the rows here, 1, 2, in fact, let me zoom in on this. This first row and the second row are this high cholesterol diet and low cholesterol diet. And the reason that we see this wording here is because of that format that we used earlier. If we hadn't formatted it, this would be a 1 and this would be a 0. But the other thing too is that Proc Sort made this 1 on top and this 0 on bottom. In other words, it's descending from 1 to 0. But the default method shows 1, 2, in an ascending fashion, and so that's why we did that Proc Sort. When reading these tables from the frequency procedure, it's important to know what's going on inside of all of these cells, and it gives you a kind of map or a legend right here on the top. So if I zoom in on this again, we can see that this first number is the actual frequency. How many subjects, how many patients did we have in this high-fat cholesterol diet with yes heart disease outcome? Or we can see the overall percentage. So among everybody, there were 47.83% who had a yes to disease or yes to heart disease and a yes to high cholesterol. But the row percent tells you of all the people in this high cholesterol diet, all 15 here, how many were this yes category. And so there were 73.33% of the 15 total high cholesterol diet that had heart disease. And then the last number represents the column percent. So here we would see that of everybody who had a heart disease outcome, yes, then there were 84.62 who had high cholesterol diets. Now those by themselves are just descriptive. They don't tell you anything about whether or not there is an association. And so if you want to test the association, you have to do a chi-square test. It would tell you between these two variables whether or not there's an association between what was expected and what was actually observed. So here right away it says the statistics for table of exposure by outcome. Now this table by itself was produced when we typed in after this table statement slash chi-squared. That slash chi-square produces this table that you see before you. And this chi-square estimate, the very first row, is your chi-squared test. Here's the chi-squared value. In fact, let me zoom in on this. Here's your chi-squared value, and here's the p-value. Here it's 0.0259. So if everything was okay, we could say right away that, well, what we observed is different from what we expected, and so there is an association. But you have to be careful, just like with all statistics, there are certain assumptions that those statistics are based on. So here you get this warning message that 50% of the cells have expected counts of less than 5. Well, when you're doing a chi-square test, the assumption is that each of these 1, 2, 3, 4, A, B, C, D, all of these cells have to have at least 5 expected cases or 5 expected counts. Well, when we have 2 or 4, then the expected counts are going to be obviously less than 5. And so this actually points to kind of like power sample size problem. So when you have this case where you get this warning, it's actually more appropriate to use the Fisher's exact test. So the Fisher's exact test is this p-value here for the Pearson chi-squared exact p-value, and it's this 0.0393. And again, this is statistically significant at a 5% alpha level, so we can say that there is an association. But you might be asking yourself, why did we have this exact statement here? Well, the exact statement for the p-chi means the p-value for the chi-square test, produces this table right here, statistics for table exposure by outcome, Fisher's exact test, and you can use a two-sided p-value, and you can see right away it's the same as that one that we saw before, Pearson chi-square test, exact, and then here's Fisher's exact test, the two-sided, and they're the same p-value, it's the same test. So in looking at it right away, you can see, okay, well, there is an association. The chi-squared is statistically significant, and so we can see that perhaps a high-fat diet is associated with a higher risk for coronary heart disease. Well, when it comes to risk, this is more of an epidemiologic concept, we want to actually find out what is our relative risk. So if on this table statement you type / relative risk, it will give you relative risk estimates in this table right here. And so this case control odds ratio row for the type of study, in this case it's a case control study, we get an odds ratio of 8.25 with 95% confidence limits right here. But the thing is, you want to make sure that you're not using just those straight confidence limits, that you're actually using the exact confidence limits. And so you specify this exact on the odds ratio, and you'll get this last table at the very bottom right here. Now this table shows you the odds ratio estimate as before. It's similar, it's exactly the same actually, 8.25, but it also gives you these exact confidence limits, which are very, very different. Now the thing with odds ratio is if you include a 1 in the confidence limit, then you can conclude that it's not statistically significant, because a 1 would say that the odds of having CHD are not significantly different from the odds of not having CHD, so there isn't really an association between that exposure and that outcome. So it's important to know which test you're using and what's going on behind the scenes, because one conclusion might be given to you. Here we would see, oh wow, high cholesterol diet would result in a higher risk for coronary heart disease. But if we make sure that we're using the right statistic because our assumptions for chi-square weren't met, then we can get exact confidence limits and see that, okay, maybe it's not the case. We need more people, we need a higher sample size to really see if that is the case. In this case it probably looks like, because you can see that the upper confidence limit is way out there and the lower confidence limit is almost 1. But anyway, that's another tale for a different day. So I showed you that this was the first method of the data input, where you have each of these cases and how many counts there were in each cell. I'm going to show you also that the second data input method is just doing the same thing, but you can see now we have to list every occurrence of that exposure outcome scenario. And in this case, because our sample size was 23 subjects, we're going to have 23 rows, 1 row per subject. And this might be something that reflects more what you would see in the real world, where you have 1 row in your data set per subject, and you have 1 exposure and 1 outcome variable that represents whether or not they were exposed and whether or not they had the outcome. So I called this data set data FATComp2, and if I run this and then sort as before, I can show you now that we can do that same Proc FREQ and get the exact same results that we saw before. Here we can see our 0.393 Pearson chi-squared exact p-value, as well as our exact odds ratio, our relative risk confidence limits as before. But the thing that we got to avoid using was this weight statement, because now the data set wasn't weighted on a count. We didn't have any kind of weight variable, so we don't need this statement at all anymore. We can just go ahead and say we want a 2x2 table of our exposure by outcome, and we want to do a chi-squared test. Furthermore, we want to get relative risk estimates, and we want to get the exact Fisher's exact method on the p-value for the chi-squared test and for our odds ratio confidence limits. We can add a title to make it nice and pretty, and we can go ahead and run our 2x2 contingency table analysis. So that's pretty much it. I hope that helped. Tune in next time. Thank you.